All right, friends. So today we are going to look at the addition method and the quote unquote, I'm doing air quotes right now, subtraction method, right? Different teachers will teach us in different ways. I generally don't encourage explicit subtraction, right? We will do something else instead. But before we do that, let's recap our substitution method, right? So last video that I had made before this one was the substitution method. So we said that we're going to see what it is solved for. If it was in the form x equals or y equals, that's definitely going to be a candidate for substitution. So I'm going to take this y, right? I'm going to, in parentheses, I'm going to replace with negative 3x plus 5. We said everything else is going to stay exactly as is. And I did show you also alternatively my front-running strategy where we said, well, if y is equal to negative 3x plus 5, then that would make 4y 4 of those things. So you're just kind of cutting out a step there. That would be 12x plus 20, which of course is what we're going to get after we distribute. Now just remember that if the coefficient was negative 4, that you'd have to multiply by negative 4. So this should be pretty easy then. Right, so we add those like terms here. That's going to give us negative 10x plus 20 equals negative 10. Right, so I get negative 10x equals negative 30. And certainly that will give us x is equal to 3. Now, obviously, we're not done, right? So it's like, oh, we have to check. Well, we're not even close to the point where we check, right? We still have to solve for the other variable, right? This is not a check, right? This is finishing up with solving the system. Right, the check's going to come after. Right, so we get y equals negative 9 plus 5, so y is negative 4. We're going to write our solution as an ordered pair here, which is going to be 3, negative 4. And if we want to, right, now we can run a check. So we haven't done anything as far as checking yet. So when we run a check, we said we're going to rewrite both equations, and we're going to substitute both variables in both equations. Now, depending on what your methodology or your teachers wants you to do, I generally will have my students check all of their equations, right? We always want to make sure not everything in math is explicitly checkable, right? Like an order of operations problem, other than using a calculator, it's not something we can check, right? Certainly operational things we can check using inverse operations, but anything that's checkable, I say we should definitely run a check. So there's my check of the first equation. And now we're going to make sure that the second one will work as well. Right, so we get negative 10 equals negative 10. Beautiful, they both check. We can move on. And so sometimes, though, substitution is not necessarily going to be our go-to, right? So could I use substitution? Yeah, I can use substitution in any system, right? If I don't mind dealing with some fractions, right? If you gave me 5x plus 3y equals 97, I can solve for x or y and have this nasty equation and substitute it. But what we want to understand here is that if I have a number sentence, right, 2 plus 3 is equal to 5, 7 plus 8 is equal to 15, that if I add them, right, if I add everything here, right, 2 plus 7, 3 plus 8, and 5 plus 15, that it should work, and it does, right? Because I'm really just adding, if I have a left side that's equal to a right side and another left side that's equal to a right side, then the two lefts and the two rights, the sum should be the same. And that's kind of what we're showing here, right? Since this is 5 and this is 5 and this is 15 and this is 15, adding, however the 5 and the 15 is broken up, it's going to be the same thing. So what would that allow us to do here? Well, it's going to allow us to eliminate y. So the addition method, right? So when we learn about the elimination method, which is going to be like the final algebraic video of this series, and then I'll talk about some word problems, this is the setup we want, right? This is the absolute easiest system in the universe, right? Because I have opposites. We're going to get to the point where we don't have opposites, and our job is going to be to create opposites, right? But for something like this, I'm going to say, well, if I've got y plus negative y, right, if I do what I did over here, instead of adding 3 plus 8 to get 11, I'm going to add y plus negative y to get 0, right? So when we cross stuff out, right, I don't use the word cancel. We eliminate things. And just like when we solve any other equation, if you add anything in its opposite, it will always give us a sum of 0, right? We say that it eliminates. Now I'm going to choose either equation. Yeah, first one seems like it's going to be extremely easy. right? I get y is equal to 4. And when I check my ordered pair here, we're going to get 3, 4. If I just look at the first one, 3 plus 4 is 7. 2 groups of 3 is 6 minus 4 is 2. All right, so here are my guidelines for addition. Now, this is only going to work in specific scenarios, right? If somebody said that 2x plus 3y equals 10 and 4x minus 7y is equal to 13, yeah, I could add these together, right? But what was the point? All it did was give me another equation with x and y, right? The whole goal, right, and this is going to be true for substitution also. What did we end up with, right? Our whole goal is to get an equation with just one variable, right? I can solve pretty much any equation with one variable, but if you give me an equation, even a really simple one with two variables, it's going to have infinite solutions, right? I can't do anything with it, okay? So we're going to, and then the steps after that are going to essentially be the same here. So I'm going to look at this, I'm going to say, fantastic, right? I know 4y and negative 4y, if I add them together, is going to give me 0. Negative x plus 3x is going to give me 2x. Negative 12 and 28 is going to give me 16. All right. Now, solving for the other variable is going to be a little bit more challenging now. Not that it's going to be horrible, right? If you're going to solve systems, you're going to have to do things like this pretty routinely, but it's not going to be as easy with the substitution systems where you had an x equals or a y equals. All right, but again, at the end of the day, what are we looking at? We're looking at a two-step equation, right, which hopefully we can all solve. All right, so we're going to be looking at negative 4y is equal to 4. So y is negative 1. And our solution as an ordered pair should be 8 comma negative 1. Right, if I just kind of spot check the first one, negative 8 plus negative 4 is negative 12. If I spot check the second one, 8 times 3 is 24. Negative 4 times negative 1 is 4. 24 plus 4 is 28. Same deal here, right? Should be pretty easy at this point. We add them together. 4y is equal to 12. Y is 3. Right? Probably going to be easier to use the first one, right? So this is a matter of preference. Some students are like afraid of the negative, so they're going to use the second one. I'm going to use the first one just because the coefficient of y is 1, so it saves me a subtraction step at the end. Right? Now, it's okay to get a solution that's a fraction, right? I would be a little, hesitant if I got, negative 37/45 or something like that, but certainly if I get something like negative a half 3, I think that's pretty reasonable. If I check the first one, I get 3, and then negative 2 groups of negative a half is positive 1, right? So 3 plus 1 is 4. Checking the second one, I'm going to get 3 times 3 is 9. 2 groups of negative a half is negative 1. 9 plus negative 1 is 8. All right? Now, remember, all we care about is that we're adding all the stuff that's on the same side. Doesn't necessarily have to be lined up. Right, so some students will say, hey, can I rewrite the second equation as y plus 3x? I'm going to say, sure. You're kind of wasting a little bit of your time, but if you need to see that, that's okay. But again, we're just adding all this stuff. If we go back to my original kind of numerical example over here, right, all I'm doing is I'm adding those 4 numbers, and when I add those 4 numbers, it gives me 20. I don't care how I add them. Right, so here, right, what am I going to do? Well, 3x and negative 3x is 0. 2y plus y is 3y, negative 8 plus 5 is negative 3, and it becomes nice and easy. Now, if they're not on the same side, different story, right? But if they're on the same side, we can do it. So I'm going to use the second equation, right? You notice that I'm always rewriting the original. I'm not just straight substituting it. Also, if you move terms, you're going to want to go back to the original equation, not the one where maybe you move some stuff around, just for the consistency's sake. Right, so we get x is 2, and we're going to get 2, negative 1. Sorry, that's supposed to be a 2. Let's try that again. A little more satisfying looking 2, marginally at least. 2, negative 1. Okay. So sometimes we have a setup like this, right? So could I add them? Sure. Except 2x plus 4y equals 10 doesn't help anybody. Now, some teachers teach subtraction, right? I don't. Right, and the reason I don't teach subtraction is when we have something, let's say, let's say I had negative x minus 4y equals negative 7, 3x minus 4y is equal to, or negative 3x minus 4y equals 12. probably a quarter to a half of my students, when they do the subtraction here, are not going to subtract negative x minus negative 3x correctly, right? Now, if you're savvy and you're really tight with your integer rules, then sure, by all means do it. With the one that I'm doing here, sure, by all means do it, right? X minus x is 0, 3y minus y is 2y, 9 minus 1 is 8. Right? That's not really my go-to because, again, the more negatives you throw in there, the more we end up making mistakes. So what am I going to do? I'm going to try to set up my opposites. Right? So what I want is, as we've seen in all the previous 4 or 5 examples, if I add opposites, I eliminate that variable. So what am I going to do? I want one of those x's to be negative x. The y is going to be problematic, right? We can multiply negative 3. That's the next lesson. So I'm going to negate everything. I'm going to take the opposite, right? Negative 1 is really, a negative is negative 1. It's the opposite. So the opposite of x plus 3 equals 9, if I multiply everything by negative 1, right, it's going to look like this. So now I've got these two equations here. And I'm going to add them together. And sure enough, we eliminate x, right? So you're going to say, oh, wait, it was easier when you just subtracted them. Sure, it's easier when we subtract them if everything is positive. So the lessons I do on word problem systems, where generally we have positive coefficients, yeah, I do model some of those using subtraction, right? So we'll talk about that when the time comes. But for today, we're going to just kind of think about multiplying negative 1. And the other thing this does is it sets up the true elimination method. Right? What if negative 1 isn't going to work? What if I have to multiply by a different number? What if I have to multiply both of the equations, right? So that's like the true elimination method. Right? So we get negative 3, 4. Pretty easy to check. The first one, negative 3 plus 12 is 9. The second one, negative 3 plus 4 is 1. All right, same thing. Right? Adding isn't going to help. It's going to give us 2x plus y equals 14. Could I subtract? Sure. We're hopefully not going to make a mistake with 2y minus negative y, though I know plenty of students that will. So what I'm going to do instead is I'm going to multiply by negative 1. Right? So then the question becomes, well, which one do you multiply by negative 1? Well, really, I guess in this one, it's probably easier to multiply the second one. But just for laziness' sake and for not having to rewrite both equations, right? Like to bring down the other equation underneath, I'm just going to multiply the first one, right? Because at the end of the day, it's not going to make a huge difference, right? So I'm going to multiply all my terms by negative 1, which again is like taking the opposite of that expression. Think about when we subtract polynomials and we distribute the negative. And of course, x will eliminate. We get negative 3y equals negative 6, right? We get y is equal to 2. And I'm probably going to go with the second one. All right, so we get x minus 2 is equal to 4, so x is equal to 6. And that's going to give us 6, 2. All right, and we should be able to do then the same thing here. Right, so if I multiply either equation, well, let me do the other one this time. Right, so let's multiply, and this is what I was talking about with laziness, right? So if I distribute the negative, I get negative y minus 3x is equal to positive 2, right? Because again, we're distributing negative 1, which in essence is changing all of our signs. Now what do I need to do? I need to bring down this equation. Right? Now I didn't need to do that before, right? The difference was the equation was already there, right? Because I was multiplying the first equation, and then I was just saying, hey, let me just keep this one the same. I don't need to rewrite anything. So it's really just a matter of preference. It doesn't make a huge difference. Now we use our addition method. Negative y plus y is 0. This gives me negative 2x. This gives me positive 8. Right, so we get x is equal to negative 4. I'm probably going to go with the first equation. Right, so if x here is going to be negative 4, I'm going to get y is equal to 10. And we get negative 4, 10. Right, if I look at the first one, 10 plus negative 4 is 6. If I look at the second one, 10 plus negative 12 is negative 2. And let's look at one more. All right, so this is one where, my experience has been students, middle school students, tend to not like the substitution method for whatever reason, which is interesting because I know in other parts of the world, like Europe and parts of Asia, they sometimes will only teach the substitution method, right? Because they're better with fractions, so they don't mind if y is equal to 3/5 x minus 19/5, let's say. They don't mind plugging that into the other equation, whereas we tend to have a tougher time with fractions here. So this is a very easy one. We did this one. I did this in a previous lesson with substitution. But if you don't want to use substitution, you can multiply by -1. Now, this would not really be my go-to necessarily, but I do want to show you a couple things. There's a couple reasons I like modeling this. One is because sometimes you do end up with nothing on one side, right? So the question becomes, well, what does that mean? Do we move the equal sign? Well, a lot of times we do that, but it's wrong, right? So we end up with 0 equals -x minus 9. So the easiest thing to do here, I know we're taught to isolate the variable, but if you add 9 on both sides, you're then going to have to divide by -1, right? You're making a one-step equation into 2 steps. So sometimes it's easier to move the variable. We get x is -9, and if I plug that in, let's say the second equation, -9 minus 5 is -14, right? So we end up with -9 comma -14. All right, so that's what happens if either we have the perfect, we'll call this the layup setup here, right? Which is, this is perfect, right? This is perfect. What happens if it's not so perfect? Well, sometimes we want to make it perfect, and we can do that by multiplying by -1. What if we have something that's not, right? 3x plus 2y and 5x minus 4y. That's our next lesson on elimination. It's going to be very similar to what we did here.